it's like it became customary that on this conference I'm like giving a talk not about biology, about computer science. It's logical because I'm a computer scientist and somehow Adam accepts this. So yeah, so today I'll like want to give you some other perspective on how vocalizations can be like taken into account as an observation, as something that we can build models on. And like to do this efficiently, I will connect with something that I'm working on currently, like to make some better machine learning tools to like model and analyze populations. Yeah, so that's the introduction. And that's why we have populations here. So I like to have some terminology adjusted. Let's say that like in every machine learning problem, we have some observations that we have. For instance, in case of recordings, those will be recordings of sounds in some context. So these are experiments, these are animals, stuff like that. Right, and we describe observations by features. Right? So traditionally, like features were some numbers, like I don't know, like the number of calls or the body temperature of a mouse, something like that. So as science have progressed, we have like better observation methods. So we also have more complex features, like we're looking at pictures, at recordings of audio. We're looking at some complex anatomical or neurochemical parameters. So we are like going both in this direction, but anyhow, we have always to remember that like feature is what we think of an object that we are analyzing. Yeah, so there is like an operational problem with like learning on population. So I will go back to it, but we can think like that we are not looking at episodes on their own, but we're like looking on the whole recording. So there's like a problem that each recording, if a recording is an observation, it would have different size, right? We can have a recording with 10 vocalizations, and we can have a recording with 1,000. Right? And this is like the problem of like unequal cardinality. So cardinality is a fancy word for size, and this has been like tackled recently because like we wanted to have machine learning on sentences, right? So like sentences have different length, different number of words. So there were some ideas how to integrate many objects into one observation, right? So as I wrote in this last point, often the problem with like unequal observations, the problem that observation is composed of some sub-observations that are fixed. Yes, and the like solution is something that can be generically described as a mathematical object, which is called a sponge, right? So this is a real term coming from cryptography, actually. So the sponge is an object that we can like soak with some data. So it has this soak operation, and it has some internal state, and it also has an operation of like squeezing out. So you can get information in, and you can get information out, some other thing. Yes, and the problem is that both soak and squeak can only use this internal state. So like we can like pack as many information as we like. And this is what we're usually doing in this setup. And so we're soaking, but the only thing that changes is the internal state of this sponge, right? So it's not like a physical sponge that will just explode with water. We'll just keep on soaking. And then we are squeezing this final embedding, let's say, or a code of our complex observation. But yeah, it's like if we're using it in this pattern, so we are first soaking, then soaking ends completely. It will not never ever add any word again, and then we will like squeeze information out. That's it doesn't matter how many things will squeeze out, it will only have the same amount of information as internal state. So all of the like recurrent neural networks, let's say LSTMs, so this long-term, short-term memories, or the newer transformers, like they all follow this general structure. So they have this limitation, like that. Effectively, they are all collapsing this to the same amount of information. And especially like the change that have made like ChatGPT possible is that like those naive sponges from early days of recurrent neural networks were like not really looking into what's soaking in, right? So the revolution that changed the paradigm was the introduction of something called attention. So like we have made a model look at different parts of the complex observation and the different with a different okay, just attention, and like this compensates. But the problem with both of those approaches is that they limit the effective cardinality. So like they can process a sentence, like they can process a book if we have like tons of GPUs and like millions of dollars to pay for the electricity bills. But this is not a practical approach like, to understand, I don't know, a recording of vocalization that contains like thousands of episodes. And this is like a total overkill. Yeah, and so back to okay. So the bottom line of this first point is that we need something different. Like so, there is a place to find some other algorithms. And okay, and so this is this use case of USB. So this is from a paper by Pavitska et al., which was actually using data from Knapska's lab, Professor Knapska's lab. So this is something we have shown. So earlier, this is like this social buffering problem. So we have some rats that were in pairs, and one was like food shocked. So those blue points localization before food shock. Red points are after, and we have this standard, let's say, embedding of vocalization. That we have time here on this axis, and here is the frequency, the dominant frequency of this. And like what we can see here is that like there are some populations of calls that are pretty evident. Like here are those 50 kilohertz, here are those 22 kilohertz calls. So this is evident. There is also evidence that like different groups in this experiment has some differences in let's say occupation of those states. Yes, so we can like reason about the whole recording just by looking at its internal structure, like without thinking whether this dot is like short or long 22, or whether these are complex or simple, or ups or downs or trills or something like that. So although this like loses information, we can make it extend, and this will be also later. So first, I would like to discuss like why is this thing that I'm constructing better than inferring individual codes. And there is some example from my different machine learning work. So this is for renewable energy, a typical example that's like pretty good. So this is a question like that, okay, so our task here is to predict the output of a wind turbine, let's say for next day. So we have a weather forecast, and it has wind speed, but we know that this wind speed has some problems that we want to fix with machine learning. So the usual approach, which people start to do when approaching this problem, is to just predict better wind speed with machine learning, and then to convert it into output power of the turbine using this simple model that actually works for most turbines. And to describe it in a second is that for some low wind speeds, the turbine produces no energy because the energy of the wind is too slow to move the wings of the turbine, so nothing happens. Then when the wind increases, the energy production also increases up to some saturation point, where it doesn't matter how fast the wind is, it's the same output. And at some point, the wind is too fast for the turbine to operate, it will just explode. So that's why the systems stop to prevent damage. So there's a question should we predict wind speed, or should we predict turbine power? And it's more obvious to predict wind and move it through this picture because it's simple, because it's true, because we want it, we believe in this model. But the problem here is that we're messing up with the attention of the model, and we're effectively losing the efficiency of the machine learning approach, because doing an error in this range, or in this range is totally irrelevant, right? If we let's say this is 20 meters per second here, so we can have 40, so this is a huge error, and it's totally irrelevant because the turbine is off. The important part is this range of the wind speed, and so it's in fact, if you do a model on turbine power, it's way more stable, it's way more useful than the model of wind speed that is converted to turbine power. Yes, so to sum it up, to be efficient, it's always better with ML to solve the main problem, not to make it some magical glue that we have some pipeline that we're accustomed to, and the one part is something that causes problem, so we're dropping it out from manual intervention, we plug machine learning there, and we believe that's it's okay, right? Yeah, so that's why I don't like approaches like that we have. That classification of calls is hard, so this will just switch it up to machine learning, and then we hope that our traditional pipeline of thinking with episodes is now machine learning enhanced, but still better. Right, and the other argument is that that would be reasonable if the output would be useful, right? So if we would believe that trills are something important, like those frog calls by Fabrice, right? So if they are episodes that are important, it would be important to be able to identify them easily, right? But actually, for most episodes, we don't know the biological context, so we don't understand the language of mice or rats, so it's not actually useful. The useful things are the states in which animals emit those vocalizations, not themselves. Right, and to continue on this line of thinking, so this is a quote from a short Netflix movie that made some noise recently. So to catch a rat, one has to think like one. So yes, we see spectrograms of calls, but we don't know what animals hear. Right? So yeah. what we're doing, we're thinking that like those things like clusters. So that's why we believe that they are entities, right? Well, this is this canonical approach to creating entities, that we see something that clusters together. So we think those are objects that are inherent. But the problem is that the similarity is something that we plug in. Right? We have decided to use spectrograms to think about the visual similarity. And this is not necessarily fundamental, right? So maybe it's fundamental, maybe it's not. Like we know that the discrepancy between 50 kilohertz and 22 kilohertz in RAS is fundamental, because we know there are different circuits driving those two phenomena. But we don't know about the rest. Yes. So to be sure that something is fundamental, we have additional arguments with those circuits, or that we have something that reappears all over the place in independent studies, which is something that we don't have in those alphabets of 50 kilohertz also. And so the very fact that we cannot easily agree on something is like a problem, and let's say a negative diagnostic outcome in itself. Right. So let's say so ontology survival tip in this situation is generally to go outside of our box of entities and try less entities with more properties than more entities with no properties. So we have some properties to describe calls. So we have stuff like length, fundamental frequency window. This is something that we all use. So it's something that I have heard is hard to describe is trillness, but it's actually not. There's something called numericity. It's which is just a length of a fundamental frequency line up to its endpoint distance, and this is a pretty nice parameter which works very nice and describing complexity. We can describe harmonics and jumps with spectral spreads or spectral entropies. There's also something that's probably overlooked in our works, which is the envelope of a signal, right? Because we know that it's not uniform, but we usually ignore it because it's partially because of the experimental problems, because of the characteristics of microphones, but it actually might be important. And this is also a research problem. And it's actually a part of a spectrum, but it's a part of a spectrum that we don't see, right? Because those are frequencies too low to be touched by 1,000 points FFT. Yes, so we should look into envelopes. We can also describe neighborhoods of calls to have context information, and a call can be presented this way. The view here is that this is very similar to flow cytometry results, right? So in the flow cytometry, we get a sample of blood, let's say, and we observe all the cells in this sample, and we give them a coordinating multidimensional sample because of their properties. And then we can reason about populations that exist in the sample. And a few years ago, we have made with my students an algorithm that actually does it automatically. So I can learn on this data. So I don't have time to look into it. This is some benchmark results, which are pretty standard for flow cytometry. And the one important thing here is that there is a benchmark that probably doesn't make sense, and this model verifies this by giving giving an answer that's negative. So this is something that's good about like decision-based models, because like let's say neural network models never give negative answers, and decision like that. And this is like an example of how does it work on a toy input where we have some population shifted. And the other nice things about it is that it is explainable in the sense that it can tell you what have changed. So this population and also that's just the final words. And the important thing is that it retains the original coordinates. So like if we do a Tisne model or a mapping of a multidimensional space, we are losing its original context. So we don't know like what this localization actually mean. Yeah? So here we still can like infer like the trillness, or let's say or frequency. So I have tried this on EEG data. It was actually pretty nice, because it can also like, find the context of electrodes on the scalp. I don't have this data here, so I'm just finished on this point. So expect some results in the future. And thank you very much. Brief, but like
So I know it's quite complex, but are there any questions? It is, yeah, all right. We got 3 questions. Wow, super cool. Alicia was first, so then Deva.
Thank you for your talk. I was just wondering, you mentioned Fourier transform parameters, generally spectrum calculation parameters. Have you experimented with various frame lengths in spectral calculations? I'm just wondering because, you know, to have precise spectrum, you need the frame length short enough to assure stable sum. So I'm just wondering if you tried various window lengths just to see when the spectrum looks best.
So like I haven't, because like as I told you before, like this is even not half baked, it's totally unbaked. So I haven't made any calculations. In fact, yeah, but generally there is a thing about spectrums that it's maybe worth saying, that like I think that we should look into parameters of sounds more than spectrums. Like, because there is, for instance, all the models that we have seen, like it's popular to DeepSpeak or what we have seen earlier. Like it's popular to make CNN on a spectrogram. So this has this one problem that like spectrogram looks different with different parameters, and so like a switch of a windowing function can have dramatic impact. But it's also like stupid because CNN does convolutions, and convolutions on already Fourier transform data is like, as everybody knows, or maybe everybody should know, this is just multiplication, a vector multiplication in a normal space. So if you're doing CNN on a spectrogram, you're just multiplying the normal signal with some data. So this can be done with much simpler neural networks than those used by DeepSpeak, for instance. But like I obviously understand the argument that like this, it's easier to like use things that exist, but anyhow, there's a room to improve here. So what I'm proposing is that to look into parameters that less more robust, less dependent on the parameters of the analysis. hope this answers the question.
So next book. I have following questions from differential signal analysis theory. We know it's a very important random signal analysis if you start the initial and boundary conditions. And also machine learning good works for stationary and semi-stationary signals, but we have random signals and nothing stationary. And also the functions are not always analytical and periodical. How the machine learning going to work if we have all these different environmental conditions, change all kind of boundary and initial condition.
Yes, so like in this framework that I'm proposing, like this is not really important, right? Because we're not doing global models. We're making, because like the transformation from sound to this multidimensional space, this is fully deterministic, and this doesn't depend on data and does not involve machine learning at all. Like we're only learning about populations that exist in the end. So that's why we don't have this local analysis. And like about spectral characteristics, like here I want to use the fact that like the physical apparatus that generates vocalization, like it's like a flute, right? It can only create single frequency, at most with some harmonics if it's probably not working as intended. But this is a speculative topic. So like we can, in fact, I believe in fact that we can think of vocalizations as like regular notes in some, let's say, instrument conditions. So it only has frequency and some spectral parameters, but it is like locally stationary signal. So that's why I don't think it's a problem.